This isn't the entire story. You still have 2 more parts to go. So, the main thing that we want to do with the project, we did a subset of a bigger project, which I'll explain in a bit. But the big project's goal, it's called the GlueX project, is to study the forces and bonds and interactions between quarks. Quarks are elementary particles. You might think of subatomic particles, like the proton and the neutron are the smallest things. You can't divide them anymore. But that's actually not true. Quarks make up protons and neutrons. Quarks make up actually 99% of all matter that we can detect so far. And quarks form, 3 quarks form a proton and 3 quarks form a neutron. And you have protons and neutrons inside the nucleus. Now the question we want to answer is, whereas protons have a positive charge, I'm sure you guys have learned this in chemistry or physics or a general science class, and when you have 2 positive charges close together inside a nucleus per se, they repel each other. And the question that we want to answer is, why don't they? Why doesn't the nucleus fly apart into a billion different pieces when you bring these 2 positively charged things together? To begin describing this, we have to look at something called the standard model. This is a list of particles and their different attributes and that we have to describe. There's 3 different types of particles. There's quarks, there's force carrier particles, and there's leptons. Quarks, like these, make up the proton and the neutron in the atom, and then we have the electron, which has much less mass in the leptons. But for our discussion today, we're only going to focus on the quarks and the force carriers. Quarks, as I said before, make up protons and neutrons. There are 6 different kinds. There's the up charm top, down strange bottom. Their names are a different story in itself. The up charm top quarks have a 2/3 positive charge, and a down strange bottom quarks have a negative 1/3 charge. Now the only quarks that we really care about are the up and down quarks, because they are the ones that form the neutrons and the protons. Quarks have color charge, which I'll discuss in a moment. It has nothing to do with the labeling of the colors here. It's just an abstract way of describing them. Quarks in groups of 3, such as in protons and neutrons, are called barons, and a quark-antiquark pair is called a meson. Now what is an antiquark? We've probably all heard that in science fiction or Star Trek or things like that. Well, here's a diagram. You have the neutrons, the protons, the nucleus, and inside the neutrons and the protons are quarks. So what is antimatter? Antimatter is a particle which, if I'll give you an example, an electron has a negative charge, and an antiparticle, which is called a positron, to the electron is a particle with the same exact mass as an electron, but has a completely opposite charge. It has a +1 as opposed to a negative 1. When a particle as an electron or an antiparticle as a positron come together, they annihilate and turn into pure energy. The opposite can also happen. Out of energy, you can get a particle-antiparticle pair. Force-carrying particles, which is the other kind of particles that we have, are particles that when 2 bodies exchange these, such as 2 atoms or 2 quarks, exchange these kinds of particles, it creates one of the 4 fundamental forces in nature. The first fundamental force is the electromagnetic force, your magnets, current. That is created by the photon. When quarks and other particles exchange photons, they're creating an electromagnetic force. That's what the photon carries. You can see here you have an electron, and a photon goes between them and repels because light charges repel. The next kind of force is the electroweak force, which is like the electromagnetic force, but at only small distances. These particles are the W+, W-, and Z particles. But for our discussion today, we don't really care about those. The other two force-carrying particles are the graviton and the gluon. The graviton is a theoretical particle. It has not been discovered yet. But physicists believe that it's a particle that, when exchanged, creates gravity. Planets and stars pulling each other, so stuff like that. Now, the gluon, which is the most important one for our discussion today, is a particle responsible for the strong force, responsible for keeping the nucleus of the atom, keeping quarks together. The strong force we're going to pay particular attention to is the strong attraction between quarks in nucleons, such as protons and neutrons. When quarks exchange these particles, it creates what's the strong attraction between these particles. Now, what keeps the nucleus together is the residual strong force between these quarks. So you have quarks in a neutron and quarks in a proton, or two quarks and two protons, and the strong force, the residual, holds them together, whereas the electrostatic force pushes them apart. It holds them together and overwhelms the electromagnetic force. Like the electromagnetic force, the strong force has a charge. It's called a color charge, and it's nothing to do with the coloration of the particles. But it's an abstract, it's turning an abstract idea into something that we can visualize. All quarks have a color charge. Antiquarks have an anti-color charge. And gluons, the force-carrying particles for the strong force, have both. And there's 8 different combinations of gluons, of color and anti-color. When quarks exchange gluons madly, a color force field forms, just like the electromagnetic field when you have a magnet and it bends electrons, things like that, field. When quarks move away from each other, the concentrated stream of exchanged gluons forms. And as they pull apart more and more, their energy increases. And like I said before in the antimatter slide, out of that energy we can create another particle-antiparticle pair, just like seen here. We have 2 quarks, and then they're pulling apart, and another pair of quarks comes out of the energy created, and they fly away.